Today I'd like to pick up where we left off. Today I'd like to take a closer look at those moving vectors, ET and EN. We call those path basis vectors. And if we stop and think a little bit about the path and what it means, how it works, we can come up with some relationships. First, we remember that S is the distance along the path, in which case the velocity of any particle moving along it is simply ds dt, distance divided by time. And if we want to understand ET, we know that's the velocity vector divided by the magnitude of the velocity vector. We've used this plenty of times defining unit vectors. Another way that we could see that is that's dr ds. Another term that we can define is k. This is the change in the tangent line, or det ds. That defines En, and with that definition we can then say, well, that means that En is k over the magnitude of k. Now you can see there's a good correlation between the change in the tangent and the radius, the oscillating radius. That brings another definition, rho equals 1 over k. And because the radius is always positive, there we have a magnitude. So if we wanted to combine that information, just for, not sure if this is for clarity or confusion, but if we wanted to combine it all in our path diagram right up here, it would look something like this. This is one area where the colors are rather helpful. And we imagine that it also has some radius, rho. So in summary, we've fleshed out a little more of, today I've fleshed out or established a couple more of the equations that relate En and Et to the overall particle's path, its velocity, its acceleration. The information in the two boxes is a lot to swallow, but it does give us what we need to identify position, velocity, and acceleration along a constrained path. In our next video, we're going to get a chance to apply this information and solve for position, velocity, and acceleration of a constrained particle. I look forward to seeing you then.